morning. So, first we will go through some case studies to understand the problem of noise, and then we will get into the techniques to remove them. So, first we will take the example of event related potential. Now, this event related potential, or in short ERP, we are getting two curves. The passive one here, that this one is the curve with lower magnitude, that this one is passive. Okay. Now, and the active one is the one drawn in a thicker line. Now, the difference between these two is that we have that these signals are EEG signal, and in EEG we are performing some test of listening. So, that the first the subject is told to listen to some tunes passively. That means, they will just listen to that, and because of that some that in the parietal lobe, that there would be some changes in the EEG signal, and that is the passive signal, that there is our brain is working, listening to it and recognizing there is a tune played. So, for that a signal is generated. Now, in the next case, where the active actually signal is collected, that the suggestion is that out of these two tunes, one is a rare tune that is played only say 20% of the time, and other is the dominant tune or more frequent tune, which is played 80% of the time. Now, at the beginning of the experiment, the subject is actually given the introduction that which one is the rare tune, which one is the more frequent tune, and after that that subject is instructed to count only the rare tunes. So, now that subject not only listens to that tunes, but the subject has to distinguish that which tune is played and keep a count of that. Now, due to that added activity, there is a change in the ERP signal, and here we get that this is the signal is generated, that is active, and here 0 is the point where actually the tune is played. Okay. So, after listening to that with a delay, we get the change in the EEG signal. So, though it is a EEG because of that it is evoked by a response, that it is evoked by a stimulus, that is why the name has come as event related potential. Now, next we will see that what kind of actually challenge we can get in this signal. That when we record the signal, the first kind of actually set of noises are the high frequency noises. Now, what are the sources of high frequency noises? We know that there are lots of sources, like the mobile towers. When you get a call in your mobile, you see that the nearby that recording device, it picks up some noise. These are all high frequency noises. If you have a pump and that operates, sometimes it creates noise. If you have say DC motor where the commutator is used, that the breaking of current makes a lot of high frequency electromagnetic noise. So, all these are source of this noise, and we are actually embedded in that noise. So, whenever you are recording the signal, that recording leads, they acts as an antenna, and that the noise induced on it get actually rides on that signal and get recorded along with the signal. So, that these high frequency noises are nowhere contributing to the signal, they just obscure that observation. So, we would try to remove them. The second kind of noise, that is our motion artifact, is a special feature for the biomedical signal, where high frequency noise is there for any kind of recording, you can face that. The motion artifact comes from that fact that usually we use actually patch sensors, they are actually added on the skin to collect the potential, whether it is ECG, EEG or EMG. We do not prefer that invasive kind of that probe or needle kind of sensor. So, the patch one is better, it does not hurt the subject. So, when the actually patch sensors are actually stick on the body, due to motion, what happens, the pressure between the patch and the skin, that changes, and that gives rise to change in actually the resistance or the contact resistance between them. And because of that, what we get, that there is actually change in actually the signal, which is of very low frequency in nature. Below we see that there is an ECG signal, and it seems it is riding on very, what we would call that low frequency some signal, and this is the baseline is moving or wandering, we say, or sometimes because of the motion there is a abrupt change and the baseline simply moves, we are moving in one place, suddenly it moves to other place and it goes like that. So, all these things are the baseline wandering, and that what we is caused by the motion, and that is why they are called as motion artifact. Next, we get another prominent kind of noise, that is power line interference, and power line interference is 60 hertz in United States, and in Europe, in India, these places we have 50 hertz. That in both this case, these signals are much lower frequency compared to our communication signals, but they are very well within the band of our biomedical signals. So, we need to think about them and how we get them. That when we are recording the biomedical signal, we are in a room, and wherever the civilization is there, that now that electricity is there. So, that we have the electrical lines, and that acts as a source of that the electromagnetic interference at power frequency, and the leads we actually use for the recording of the biomedical signal, they act as an antenna and catches that electromagnetic noise, and that interference gets recorded or get added with the biomedical signal, and we always get a 50 hertz or 60 hertz power frequency hum along with the signal. Again, this is not the native characteristics of the biomedical signal, which hampers actually the analysis. So, we need to find a way to remove them. So, next we look for other kind of interference. Now, here we should first make it clear that what is our signal and what is our noise. The fact is, what we are interested in is our signal, and what we are not interested, that is our noise. Otherwise, that would be the only definition, because when we see that something is signal, that for other, that may be a noise. For example, when we are actually in this classroom, we are listening to the lecture. Now, if there is any tune played outside and you like that music, then the lecture could be a noise to you, but those who are interested in listening to the lecture, for them that the nice tune that is played outside, that may be the noise. So, it depends on your actually focus or interest. Now, in this case, in this particular example, we have taken two signals. One is the ECG of the mother, that we write as MECG, and that mother is carrying a baby in the womb, that is called FECG. Now, we may be interested in the health of the fetus. So, in that case the mother's ECG we would say is interfering or the noise. Your focus also could be to the health of the mother. In that case, you will tell that the fetus ECG is interfering with the mother's ECG and we need to remove it. So, depending on your focus, you select that which is your signal and which is your noise, and such interference may occur. And as we see here in this case, that we see that these big beats are for the mother's ECG, and the small beats which are shown separately here also, that they are because of that fetus. And another thing we note that the fetus, the ECG beats, they are much closer. That means, the heartbeats, the rate of actually that pumping is more in case of that fetus. In fact, there is a peculiarity in nature, bigger the animal, the heartbeats are slower. The smaller the animal you take, you will find the heartbeats are actually faster. Now, here in this case we are just getting for the same species, but the womb actually is having higher heartbeats and they actually added with each other, and it smears the signal. We do not get the real nature of the mother's ECG. So, if we have to study mother's ECG or the fetus ECG, then we need to actually remove the other. So, this is another kind of noise we got, and now we need to look at that what could be the ways that we could get rid of them. Now, first we go for the time domain filtering. The time domain filtering, it has the biggest advantage is it is fast, and we would say that it is faster than all the other techniques we know. Then another advantage it gives, that it does not demand a lot of things. Many times that when we go for the filter design, we would ask a lot of questions, that please tell us that how is the noise, what is the spectral characteristics of it, what is the strength of it. So, all these questions would come, but in case of the time domain filtering, no such questions are asked. We do not need any particular actually that information about the characteristics of the noise. So, that makes it easy to apply them. The only disadvantage is that there is no control on how it will work. Actually, it works based on some very simplified assumption, that if any high frequency noise is there, then if we do smoothing, then we can get rid of the noise. So, it actually works on such simple principles. So, we do not have actually control over it, the very actually loose control over the process. We can do more smoothing or less smoothing, but we cannot actually customize it depending on the situation at hand. Okay. So, let us see now that how is the form of the signal. So, here we show the first example of synchronized averaging. That is the first example of the time domain filtering. Now, I hope you recall that we took that example of that throwing a die. So, here we are talking something very similar, that we have the signal x k with which that the noise n k is added, and because the noise is added, what we can observe, that is y k. We cannot get access to x k directly, and our intention is to actually get rid of n k, the noise component. So, in this case, if we have multiple ensemble of that signal, that means if we have multiple examples of that signal, and then in that case that we use that index k to denote that ensemble, and m is actually keeping the time index. Then what we can do, we can sum all those ensembles, and if we sum them, what will happen, that when we look at the first term here, that the signal component, when we add them, we get the signal components, they will add up, and that will we get m times of the signal. And to get that, actually one thing is very important, that we need to align the signal properly. Without that, we cannot actually get it. And when we look at the next term, that is the noise part, that summation of the noise. Now, what we will get? It will give us the mean of the noise, or m times the mean of the noise, and if the noise is 0 mean, which is the case for most of the signal, the high frequency noise, the power frequency noise. So, all the high frequency or power frequency noise, they are 0 mean, then as the mean is going to 0, then this sum will go to 0. However, it has some variance. The variance is not going to 0. When we take the sum, the mean is going to 0, but the variance is, we are getting the m times the variance of the original the noise. But because our that signal is multiplied or scaled by m times, so variance of the signal or energy of the signal would go up by m square time. So, there is a improvement in the SNR, and here we get that for the observed signal y, after the summation, that we get the SNR improved by square root of m times. So, if we could actually add up this signal by synchronous averaging for 100 times, we can get the resultant SNR would be multiplied by 10 times. So, that would be a great improvement. Now, let us look at that what are the requirements of it. The first thing that we need to look at, that we need to have multiple realizations of the signal of interest. Now, how we can get that? For example, we have that ERP signal, we can actually conduct this experiment number of times, and we can collect that signal, and then we can actually add them up. If we think of a ECG signal, that in case of ECG, we can take actually multiple cycles of the ECG, and we can add them up to actually to make the synchronous averaging possible. So, in that way we need to have multiple signal, without that we cannot make use of this synchronous averaging. The next important point for that synchronous averaging is we need to align the signals, because without aligning, if we add them, the signal component itself can cancel each other. They would not have a reinforcement effect. So, we need to align them together, and that trigger for alignment come from different sources. First thing, that it can come externally. For example, in this ERP we are playing some tune. So, the point in time that when the tune is played, that is that here marked as 0. So, that can see this point, that point 0, that is signifying the time when the tune is played. So, that can act as a trigger, that every time we take the 0 point from where that tune is played. So, with the help of that we can actually align the different realizations of ERP. It can be done in other way also. Let us look at that the form of that ECG signal. ECG signal looks like this. So, here is a P wave, here it is Q, R, S and T, then after a long gap again it repeats P, Q, R, S and T. Now, most prominent point here and unique point is this R. So, we can take a cycle, maybe this part we can take one cycle, from here to here another cycle. So, that way we can take the different cycles and we can take these R point as the reference and we can align them. So, it can be done through using that signal also, that alignment is possible. So, we need to first find the point of each of this realization, that which can be used for the alignment, and then we have to align and add the different realizations. The third or the last step is that divide the result by the number of realizations. That means, because we have added them up so many times, the signal is reinforced by that time. So, there is a scaling of the signal. So, we need to get rid of that scaling. And in the right hand side we are showing some example that white noise is added with the sinusoidal signal. So, it is riding on the signal and we get the first one, the signal is very spiky, that. So, then if we average it first time, that means 2 realizations we take and add them up, then still it seems to be equally spiky. Now, once 10 such actually averages are performed, then we get that it has actually reduced to some good extent and now it looks more or less like a sinusoid. When we go for 100 times, then we see it is difficult to say that it is not a sinusoid, the noise had actually gone down to that extent. So, what we get, the more number of times we can have the realization of that synchronous averaging, and more times actually we can add them, we can have actually better and better answer or result out of the synchronous averaging. Now, what is the challenge in this? The challenge is that if we want to do it in say real time, then it can throw up a challenge. Usually we investigate one patient and for that patient we want to actually analyze that signal. And here if we take the ECG signal for example, from that patient, for a particular lead we need to take, we cannot take different leads and actually add them up, there would be different signal. So, we have to take record it for a long time and then we can actually add them up together and then we can get rid of the noise. But that means it becomes a block process, we are adding it up for sufficient amount of time and then we get that answer. So, as a result what is happening that it is becoming non real time kind of operation, though it is very simple and effective. So, for real time applications this is not actually the technique to use. So, thank you.